Okay, so welcome to section 3.7. Should I make that a bit darker? I wonder. Maybe I should keep it consistent. Okay, so 3.7 is rational functions. And you'll be happy to know that I have stopped reading the book again because their examples were just too ridiculous. So definition. Okay, so a rational function, that's what we're defining. A rational function is of the form f of x is equal to p of x divided by q of x, where p of x and q of x are polynomials. Okay, so let's recall the 13th commandment or the 11th. How many commandments are there? Okay. So recall that thou shalt not divide by 0. Thou shalt not divide by 0. Okay, so let's note that the domain of a rational function, so the domain, how do you spell domain? D of a rational function, p of x over q of x. I have to exclude all values for which the denominator is 0. So it's all values of x, provided that q of x is not equals to 0. So everything except those values of x which make the denominator 0. Okay, so for example, so let's find the domain of the following rational functions. So find the domain of the following rational functions. Okay, so number 1, let's say we have that f of x is equal to, in the numerator, let's do x squared plus x minus 6, and in the denominator, okay, well, let's see if I can make this autocorrect a bit better. Let's do x squared minus 2x minus 3. Okay, so we have that f of x is a quotient. It's the quotient of two polynomials, namely x squared plus x minus 6 divided by x squared. Oops, oh my goodness. Let's see. Divided by x squared minus 2x minus 3. So what I want to do is I want to factor both the numerator and the denominator here. So what two integers have a product of negative 6 but a sum of positive 1? And I claim that that will be negative 2 and positive 3. Similarly, in the denominator, what two integers have a product of negative 3 and a sum of negative 2? I claim that that will be minus 3 and plus 1. So the domain is going to be the set of all values of x given x is not equal to what two values? 3 and -1. Oops, wrong color. Because thou shalt not divide by 0. So I have to exclude those values. Let me actually put this down here. Put an arrow. I must exclude those values which make the denominator 0. So number 2. Let's say we have, actually let me move this down a bit. Let's say we have that f of x is equal to, so in the numerator, let's do x squared. It's x squared minus 3x minus 4. And in the denominator, let's do x cubed minus 9x. Okay, so once again, I would like to factor. So first I note that f of x can be written as x squared minus 3x minus 4 divided by x cubed minus 9x. So in the numerator, I'm looking for two integers that have a product of -4 and a sum of -3. So I claim that that's -4 and +1. In the denominator, I notice that I can factor out an x, and what remains is x squared minus 9. But that can factor. It's a difference of squares. So I claim, my goodness, it's 1 in the morning, there's still traffic. So x minus 4 and x plus 1 all over x times the quantity x plus 3 times the quantity x minus 3. So therefore this implies that the domain, oh, yeah, okay, I guess I should make that a bit thicker. The domain is going to be all values of x except those which make the denominator 0, namely 0 and plus or minus 3. So we must exclude those 3 values from our domain. Okay, so number 3. Let's say we have that f of x is equal to, what shall we do? Let's do x to the 4th minus 81 all over x cubed plus x squared minus 4x minus 4. Okay, so rewriting, we have that f of x is equal to, in the numerator we have x to the 4th minus 81. In the denominator we have x cubed plus x squared minus 4x minus 4. So in the in the numerator what I have is a difference of squares, namely x squared plus 9 and x squared minus 9. And in the denominator I can factor by grouping. So I can factor x squared from the first 2 terms and get x plus 1, and then a -4 from the second 2 terms and get x plus 1. Okay, so factoring, once again, the second factor in the numerator can be expanded. The first factor cannot be expanded except over the complex numbers, so I'm just going to leave it. So x plus 3, x minus 3, and then we'll have x squared times the quantity, x squared minus 4 times the quantity x plus 1. However, x squared minus 4 also factors as a difference of squares, namely x plus 2 times x minus 2. So we can rewrite this as quantity x squared plus 9 times x plus 3 times x minus 3 all over x plus 2 times the quantity x minus 2 times the quantity x plus 1. Okay, we finally did it. Okay, so what does this mean? This means that the domain of this function will be all values of x excluding those values that make the denominator 0. So x cannot be plus or minus 2, and x cannot be negative 1. Okay, so hopefully that's making sense. Let's note something though. So note for f of x being equal to p of x over q of x, if there exists a factor x minus r that divides p of x and q of x, this implies that r is still not in the domain of f of x, even though we can reduce. So let me write that d a bit better. So it's still not in the domain of f of x, even though we can reduce it, or though it can be reduced. Okay, so theorem. Okay, so the graph of a rational function. So the graph of a rational function how do I want to state this? F of x equals to p of x over q of x has, number one, vertical asymptotes. So vertical asymptotes for all values of x such that q of x is 0 given f of x is fully reduced. Or number two, if f of x is not fully reduced, it has holes at the point r comma f of r for all values of, or all factors of x minus r that divide both p of x and q of x. So if you can reduce a factor, there's a hole in the graph. And I will show this momentarily. Okay, so for example, okay, so the x and y intercepts of, or actually, yeah, let me note something first before I do this example. So note. So the x and y intercepts, the x and y intercepts of a rational function are found as previously by letting y and x be 0 respectively. Okay, so now let's do our example. So for example, so determine the factors. So determine the factors in both the numerator and denominators given the following. Okay, so number one, let's say I give you a graph, so x and y coordinate axes. Let's say we have a vertical asymptote here and here, and so 1, 2, 4, 5, 2, 3, 4, 5, 1, 2, 3, 1, 2, 3. Let's say we have maybe x-intercept at 0, at maybe -3 and +4, something like this. So let's say it does something like so. And maybe it does something like so. And then what shall it do? Let's see, maybe I'll have it do something like this. But I definitely want it to go through that intercept. There we go. Okay. So let's say this is an approximation to my graph. Okay, so if this is f of x, what do I know? I know that I have vertical asymptotes at x equals to 2 and x equals to -2. So I claim that f of x at the very least will have a factor of x minus a -2 times x minus a +2 in the denominator, because those are the vertical asymptotes. Now I have x-intercepts at -3, so x minus a -3 becomes x plus 3 at 0, so that's just, let me put that first, that's just x. X minus 0 is just x, and at 1, 2, 3, 4. So x minus 4. Now, it's not, there could be a constant multiple times this, maybe 5 or 17 or 19/5. So the way we take care of that is we say times some k, where k is some real number. So this would be an estimate to the function graphed here, because it has all of my x-intercepts or zeros in the numerator, and it has the thou shalt not divide by vertical asymptotes in the denominator, because thou shalt not cross a vertical asymptote, because it's a 0 of the denominator. Okay, so number 2. Did I state that? Yeah, I did. Okay, so number 2. Let's see, what shall we do? So let's do x and y coordinate axes again. X and y. Let's say now my asymptotes are maybe at 1 and 1, 2, 3, 4. So we have 1, 2, 3, 4, 5. 1, 2, 3, 1, 2, 3, 4. And then 1, 2, 2, 3, 4, 5. Okay, and let's say we have something that looks like so. Oh, yeah, there was something I wanted to do on number 1 that I didn't get to, so let me go back and do that actually. I said to myself I would do it, and then I totally forgot, because that's what happens when you're old and tired. Okay, so let's go back up. Notice something about this x-intercept. It's S-shaped. So what that means is that the power on that 0 is odd. So I'm just going to call it, say, 3. Now it could be 5, it could be 11, but all of the other roots are linear. They go through as little lines. Okay, and what alerted me to that was this here. This is parabolic, right? So I know I'll have to raise that to some power. Okay, and now let's do something like, what should we do? So, and then something like, so. Okay, so this is a terrible graph, but we can do what we can with it as follows. My vertical asymptotes are at x equals to 1 and x equal to negative 4. So I know that the function f of x will be written as, in the denominator, I'll have x minus a negative 4, so x plus 4 and x minus 1. In the numerator, my roots, which are my zeros, are at 1, 2, 3, 4, negative 5, so x minus a negative 5, which is x plus 5, and that root is linear. Then I have a root at minus 2, x minus a negative 2, but that's parabolic, so I'm going to call this squared, just for the heck of it. It could be to the 4th, doesn't matter. And then 1, 2, 3, my root at 3, once again, has a little line. So I have a factor of x minus 3 to the first power. And I know that there's probably an integer k that this is multiplied by. So I'll just say times some integer k, not kappa, for those who are actually listening to my lectures, where k is a real number. Okay, and oh, third time's a charm. So let's do one more, number 3. Let's say we have something x and y coordinate axes. Come on, autocorrect. Nope, okay, it's not going to autocorrect. Okay, there we go. X and y. So let's do 1, 2, 3, 4. 1, 2, 3. 1, 2, 3. 1, 2, 3, 4. Let's say we have, let's make this simpler, shall we? So let's just do one vertical asymptote. Add, what is that? X equals to negative 2. Then let's have something like this. And maybe that. Well, that's terrible. Like so. It's not a great graph, but you get the idea. And then something like so. Okay, so my f of x is going to be, this time I have a specified y-intercept. Not that it matters, but that's where k comes into play. We're going to augment k for the y-intercept. Don't worry, I'm not going to make you do that, just so you know. So the denominator is going to be simply x minus a negative 2, or x plus 2. My x-intercepts is just 1. It's linear at negative 3, so I just have x minus a negative 3, or x plus 3, in the numerator. But why did I leave such a large quotient symbol? And that's because I have a hole. I have a hole at, what color should I use for this? Let's do hot pink. So I've got a hole right here. When x is 1. So when x is 1, we have x minus 1 and x minus 1 to take care of the hole. Because they can be reduced, that's going to be the hole I was talking about here. Okay. So that takes care of the hole, and I know that in order to accommodate the y-intercept, I'll need to multiply this by some real number k. Okay, so let's note. Hopefully this is making sense. So note. So when factored, the x-intercepts are the roots of the numerator, right? So when factored, the x-intercepts are the roots of the numerator the vertical asymptotes. So the vertical asymptotes are the roots of the denominator and this is when reduced, right? Otherwise it's a hole, right? So if there's the same factor on the top and the bottom and you can reduce, then that's a hole. Okay, so where was I? So let's define horizontal asymptotes. So how do we find our horizontal asymptotes? Okay, so let f of x be p of x over q of x equal to, say, p is going to be the polynomial a sub n x to the n plus dot 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 plus a1x plus a sub 0 or a naught, and q is going to be b sub m x to the m plus dot 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 plus b1x plus b naught. Then if, number 1, the power on top, n, is equal to the power on the bottom, or the degree rather, the highest power. So if the degrees are equal, then this implies the horizontal asymptote will be at y equal to the quotient a sub n over b sub m. Number 2, let's say the numerator, the degree of the numerator is less than the degree of the denominator. Then this implies that the horizontal asymptote will be at y equal to 0. And number 3, if the degree of the numerator exceeds the degree of the denominator, then there is no horizontal asymptote. Okay, so note So if we have the case that n is larger than m, we perform polynomial long division. So we perform polynomial long division. Long division. The slant asymptote, let me underline that, is found by y equal to the quotient of that operation. Okay, so for example, so plot the following rational functions. Plot the following rational functions. So number one, let's say we have that f of x is equal to, let's do x squared plus x minus 6 divided by x squared minus 2x minus 3. Okay, so we have that f of x is equal to x squared plus x minus 6 divided by x squared minus 2x minus 3. So this is going to be, when factored, this will be x plus 3 times x minus 2 in the numerator. And in the denominator, we had x minus 3 times x plus 1. Okay, so let's see what we have. I claim that my x-intercepts will be at -3 and +2, namely the roots of the numerator. I claim that my vertical asymptotes will be at x equals to 3 and -1. I claim that my horizontal asymptote will be at y equals 2, since the power is the same. 2 is the highest degree. So I claim that it'll be 1 over 1, which is 1. Okay, so what about my y-intercepts? So my y-intercept, there should only be one because it's a function. Intercept at, well, if I let x be 0, do you agree that I just get -6 divided by -3 or +2? So I claim that the y-intercept is at 0, 2. So I can put all of this together to plot this function. So x and y coordinate axes. Let's see. Yeah, I think I'll just put it down here. Nope. Why is it not auto-correcting? Don't understand. There we go. X and y. Let's see. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3. Oops. 3, 4, 5, 6. 1, 2, 3, 4. So I always draw my asymptotes first. So let's draw the vertical asymptotes, which are at x equals to 3 and x equal to -1. Okay, Please autocorrect my terrible drawings. There we go. My my horizontal asymptote is at y equals to 1. So let's make this asymptote. Okay, my x-intercepts, let me change this to a solid line. My x-intercepts are at -3 and +2. My y-intercept is at +2. So I claim that, well, how do I know what this does? Is it above or beneath? Does it come up like this or does it come down like that? How am I going to know? And that's where we have to get into a sign chart. So before we go any further, I'm going to leave this as it is. Let me move this up a bit. I'm going to do a sign chart with the function factored. So what we do is we need to look at the factored form. We're going to do values for x. So it looks like I have 4 different values. So I have, let's do 1, 2, 3, 4. My values are -3, -1, +2. So I have a factor of x plus 3 and a factor of x minus 2. Then I have -1 and 3 as roots from the denominator. So x plus 1 and x minus 3. So what we want to do, I always take these and I write, where is this factor 0? So I look where each factor is 0. And normally you would have to plug in values. But the way I do it, I say everything to the left of 0 is negative. And everything to the right of 0 is positive. Now you can plug in numbers on your number line to show this, but this will save you a lot of time. Okay, so now 4 negatives make a positive, so that's above the x-axis. 3 negatives make a negative, so that's beneath the x-axis. So right away, if I'm to the left of -3, I'm above the x-axis, so I know it's going to be here. Then if I'm between -3 and -1, I'm beneath the x-axis, so I do something like so. Okay, so now let's see, between -1 and 2, 2 negatives make a positive, so I'm above the x-axis. So between -1 and 2, I'm above the x-axis. Do something like that. Okay. Then between 2 and 3, 1 negative is negative, so I'm beneath the x-axis. Okay, so let's see, I'm beneath the x-axis. Oops. No, terrible graph. Okay, let's see, I gotta turn this so I can draw this a bit better, sorry. If I turn this upside down, I can draw this, I think. Yeah, there we go, that's a bit better. Okay, and now, to the right of 3, all positives make a positive, which means we're above the x-axis. So, where am I? I could be here in this region, or I could be here in this region. So what I'm going to do, I'm going to plug in 1, 2, 3, 4. I'm going to plug in x equals to 4 into the equation to see. 4 plus 3 is 7. 4 minus 2 is 2. 4 minus 3 is 1. And 5. So whatever it is, it's large. It's much larger than 1, so I know it's going to be above that asymptote. So I know that not only is it positive, but it does something like so. There we go. Okay, so this is an estimate to the graph of f of x. It's actually quite pretty. Okay, so let's do another one. A couple more actually. Okay, so let's see number 2. Let's say we have that f of x is equal to, let's do x cubed plus x squared minus 4x minus 4 divided by, pardon me, x to the 4th, oh my goodness, minus 81. Okay, so what do we have? So we have f of x is equal to, and we know that this is x cubed plus x squared minus 4x minus 4 divided by x to the 4th minus 81. And for those of you that recognize these problems, they are indeed the ones I've done up here. So I'm just going to copy and paste the fully factored form right here. Copy, unless I did I do it wrong? Yeah, was that one the other way around? Oh, it was the other way around. So what can I do? Okay, well, let's see. What I can do is paste this off to the side, then take all the purple guys in the top here, put them on the bottom, make them pink, and vice versa. All the pink guys here, make them purple. No, not that color, purple. And then take this and put it on the top. And there we are. Because I think I did it the other way last time. Anyways, hopefully that makes sense. So there we are. Is that true? Yes, that's true. Okay. So my x-intercepts are going to be at x equal to -2, -1, and +2. My vertical asymptotes will be at x equals to -3 and +3, because the other two roots here are complex, so I don't need to worry about them when plotting. Let's see, what did I do next after that? I did my horizontal. Okay. What about the horizontal? Since the degree on top is smaller than, since the degree 3 is smaller than degree 4, my horizontal asymptote will be at y equals to 0 in this case. And my y-intercept, of which there is only one, is going to be when x is 0, what is y? Well, -4 over -81, that's +4 81sts, which is pretty small, whatever it is. Okay. So now let's go ahead and plot this almost before we do our sign chart. So we know we're going to, okay, so x and y coordinate axes. X and y. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, so my vertical asymptotes are at -3 and +3. My horizontal asymptote is the line, actually let me change this to solid. It's the line y equals to 0, otherwise known as the x-axis. Okay, my x-intercepts are at -2, -1, and +2. My y-intercept is just slightly above 0. No, not drawn to scale. Okay, or very well. Okay, but now I need to see what happens on either side of those asymptotes. So now we're going to do our sign chart. But the sign chart has 1, 2, 3, 4, 5 factors of real numbers. I can ignore the complex x squared plus 9. So I need 1, 2, 3, 4, 5. Nope, it's not going to autocorrect. Okay, 5. There we go. Yeah, close enough. Okay, so let's look at the factors. The leftmost root is -3, and that's for x plus 3. So the root is here. The next most negative factor is -2, x plus 2, so the root is here. Then my next most negative factor will be at -1. That's x plus 1. So the root is here at -1. Then I have my next most, or the smallest positive is 2 at x minus 2. So the 0 is at positive 2. And then finally, x minus 3 has a root at 3, so the 0 is here. I can erase all of this. Okay, so what do I know? I know everything to the left of 0 is negative. And everything to the right of 0 is positive. Okay, so what do we have? 1, 2, 3, 4, 5 negatives is negative, so that's going to be beneath the x-axis. So I know to the left of -3, my graph will lie beneath the x-axis. Okay. Between -3 and -2, 4 negatives make a positive, so my graph lies above the x-axis. Between -2 and -1, 3 negatives is negative, so my graph lies beneath the x-axis. Let me try and make this a bit better. Okay. Then between 1 and 2, 2 negatives make a positive, so my graph lies above the x-axis. So it looks like it does something like so. Very shallow, which means that the previous guy probably is more shallow. Then between 2 and 3, 1 negative is a negative, so my graph lies beneath the x-axis. So I know it's going to approach this asymptote like so. And then beyond 3, all positives is positive, so my graph will lie above the x-axis, something like so. Okay, there we are. That's a crazy graph, but there it is. Okay, so let's do another one. So actually let me move this a bit so we have more room. Yeah, that looks nice. Okay. How about that one? Does that look okay? Okay. So let's do number 3. So for this one, let's say we have that f of x is equal to, let's do x cubed minus 9x divided by, let's do x squared minus 3x minus 4. So we have that f of x is equal to, in the numerator we have x cubed minus 9x, and in the denominator we have x squared minus 3x minus 4. Okay, so we can factor the numerator as x times x squared minus 9, which will factor some more in the next step. And in the denominator, what two integers multiply to -4 and add to -3? There we are. So now we can factor the numerator as x times x plus 3 times x minus 3 all over quantity x minus 4 times x plus 1. Okay, so first let's do our x-intercepts. Intercepts, which are the roots or zeros of the numerator. And those will be at x equals to 0, negative 3, and positive 3. My vertical asymptotes will be at x equals to the zeros of the denominator, namely negative 1 and 4. Notice that because the degree of the numerator is 3 and the degree of the denominator is 2, there's no horizontal asymptote. But that means we need to do polynomial long division. So let's go ahead and do that. So we're going to take x squared minus 3x minus 4, and we're going to divide it into, what do we have? X cubed plus 0x squared minus 9x plus 0. Okay, so what do I need to multiply x squared by in order to get x cubed? And I claim that that's just going to be x. So distributing, we get x cubed minus 3x squared minus 4x, which I will then subtract from the line above, leaving us with 3x squared plus or minus 5x. Okay, so now I start again. What do I need to multiply x squared by to get 3x squared? And that would be a positive 3. So I can go from there. So y equals to x plus 3 is the slant asymptote, because that's the quotient. So we'll call it slant asymptote. Slant asymptote at y equals to x plus 3. Okay, what's next? My y-intercepts, right? So y-intercepts, sept singular, will be at 0, comma, when y, it's 0. So that's the only y-intercept at 0, 0. Okay, let's see. Wonder if I need more room. I'd like to fit this on here. Will I be able to? One, two, three, four, 5. I have 5. I don't know if I can. Well, maybe I can. I'll put this here. And I'll say slant asymptote at y equals to x plus 3. I'll just put that up there. I'll put my y-intercept over here. Yeah, hopefully that's okay. Okay, so what I'd like to do, let's first start plotting. I know I need to go to 4, 0, 3. Okay. So x and y coordinate axes. X and y. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3. Okay, so my vertical asymptotes are going to be at negative 1 and positive 4. I have no horizontal asymptote, but I do have a slant asymptote, so let me show you what that means. So that's a line y-intercept of 3, the slope of 1. So it's going to look something like so. So that's a slant asymptote. Notice it is indeed slanted. Okay. Actually, maybe I should just move this so I can make that a longer slant asymptote and show you where this is coming from. That means I'll do my sign chart off on top instead. So the slant asymptote. Okay, so let me continue this and show you why this is. Let me just finish it. So this gives us 3x squared minus 9x minus 12. And at this point it doesn't matter because we'll be left with 4x. And there's nothing I can multiply x squared by and have the quotient be a polynomial. So we're done. We know that the slant asymptote, the slant asymptote is at y equals 2, x plus 3, which we already knew, just was showing that. Okay, so now what I can do is continue the slant asymptote to where these two intersect. Okay, so now let's plot our intercepts. So where my x-intercepts are at 0, -3. Now it's okay to cross a horizontal or slant asymptote. We can never cross a vertical asymptote. +3, and my y-intercept was the same. It's still 0. So what is this going to look like? Well, I could do my sign chart, which I'm going to have to do on the next page. Oh, I'm sorry. There's just no way. Okay, so my sign chart. I have 1, 2, 3, 4. Nope, not going to autocorrect. 4, 5 roots corresponding. So -3, -1, 0. Okay, so -3, that's x plus 3 as a root there. Then -1 in pink. Oops. So x plus 1 as a root here. Then what do we have? Then we have 0. So x has a root at 0. Then we have +3. So x minus 3 has a root here. Then finally we have x minus 4 has a root at 4. Okay, and anything to the left of 0 is negative. And anything to the right of 0 is positive. Okay, so we have 1, 2, 3, 4, 5 negatives. Make a negative, so that's beneath the x-axis to the left of 3. Okay, sorry, to the left of -3. Then it'll be above the x-axis between -3 and -1. 1, 2, 3, and -1. Okay, so it's going to do something like, oops, because it's not going to cross that vertical asymptote. We know that it can never cross. Ugh, come on. Okay, well, I'm just going to have to draw it poorly. Maybe it'll do something like that. It's a terrible graph, sorry. So sorry, that really is terrible. Okay. Not making it any better. Okay, let's see. Above. Oh, come on. Let's see. Why is plotting this so difficult? Okay. There we go. Upside down seems to work. Okay. So now between -1 and 0, it's negative. So that's beneath the x-axis. So it's going to do something like so. And then, actually, I don't like the way that looks either. Then between 0 and 3, it's positive, so it's above the x-axis. Okay, then between 3 and 4, it's negative, so it's beneath the x-axis. And then beyond 4, it's all positive, so it's above the x-axis. And I happen to know it does something like this, but I don't care if you don't know that. You can plot a couple points to see that. But we're set here. Okay. So, anyways, notice that there would be a vertex here of this parabola, but it's not on the x-axis. That's interesting. Okay, so let's do one more for good measure. Third time's a charm, but fourth is because this is it, and I'm setting you free. I'm not going to make you do section 3.8. Okay, so let's do f of x is equal to x squared plus 2x minus 3 divided by x squared plus 5x plus 6. Okay, so we have, hopefully this will be easier than that monstrosity I just did. So we have x squared plus 2x minus 3 divided by x squared plus 5x plus 6. Okay, so what two integers have a product of -3 and a sum of +2? I claim it's x plus 3 and x minus 1. What two integers have a product of +6 and a sum of +5? And I claim that that's x plus 3 and x plus 2. So I claim that there's a hole at -3 comma f of -3. But I can't plug in -3 because I'd be dividing by 0. So what does that mean? That means in the reduced expression. So that's going to be x minus 1 divided by x plus 2. So if I plug in -3, that would be -3 comma -4 divided by -1, so that's 4. So there's my hole. My x-intercepts are going to be at x equal to 1. That's all that we have, right? Just what's in the numerator, and there's only a single factor in the numerator. My vertical asymptote will be at x equals to -2. My horizontal asymptote will be at y equals 2. Well, the degree of the numerator is 1 and denominator is 1, so it's 1 over 1, which is just 1. My y-intercept, if I let x equals to 0, I get -1/2. Okay, so this should be enough to start, and then I'll do my sign chart once I've started. So X and Y coordinate axes. X and Y. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3. 1, 2, 3, 4, 5, 6. Okay, so I have one vertical asymptote at -2. I have one horizontal asymptote at +1. I have one x-intercept at +1. I have one y-intercept at -1/2. I have a hole at -3, 4. Okay, so I can see what this is going to do, but let me do a sign chart just to prove that it's true. So sign chart, I only have 2 factors now. So those factors are x + 2 and x - 1. Okay. So I know I'm negative to the left of 0, positive to the right. So 2 negatives makes a positive, so that's above. So to the left of -2, I'm above the x-axis. Okay, 1 negative makes a negative. So between -2 and 1, I'm beneath the x-axis. And then 2 positives make a positive, so to the right of 1, I'm above the x-axis. Okay, so that's an estimate to the graph of f of x. Okay, I really enjoyed these. These are fun. This one, yeah, I'm not going to make you do this one. I just wanted to show you a slant asymptote for that one. So, duly noted, moving on. This one's kind of nice as well. And, of course, this one is a classic one. Okay, so there we are. Remember, what did I say? No section 3.8. So I will see you guys after exam 2 and in chapter 4.